Well, in these past lectures, we've been exploring and enjoying the golden ratio and the golden rectangle, the rectangle that captures the essence and the spirit of the golden ratio because its proportions, if you take the length of the base and divide it by the length of the height, you get the perfect number, the golden ratio, which is 1 plus the square root of 5, all divided by 2, which, again, the decimal, which you probably now memorized, is 1.618033, and so on. So let's just remind ourselves how you can actually construct one. Here's actually the construction that we did in the previous lecture, where we actually demonstrated a way of producing one. So let me just remind you how this works. We started originally with this perfect square, which here is marked by a 2 by 2 square. We then cut the bottom length in half, so each one of these is a 1. And then I took a compass and I drew an arc whose center is actually here at this midpoint, and the radius actually is this length, and I drew that arc down. So this is actually part of a very large circle. And I saw where that arc of the circle actually intersected the extended base, if you would allow me to extend the base until I have that point of intersection. I then extended the top of the square correspondingly, and then drew a perpendicular line that went right from the point of intersection of the arc of the circle and the floor up right to the ceiling. And this outer rectangle, in fact, is a perfect golden rectangle. And in fact, we proved it by looking at this math here. So for example, I remind you that we discovered that this is a right triangle where, in fact, a golden triangle, where this has length 2, this has length 1, using the Pythagorean theorem that Mike will prove up next. What we see is that 2 squared plus 1 squared, which is 5, will equal the, once we take the square root, the length of this. So this is the square root of 5. So this is actually a radius of this very large circle. But this, too, represents the radius of that same circle. So since this length is the square root of 5, this length also is the square root of 5. So we have the square root of 5 here, and this addition of 1 here. So the entire base has length 1 plus the square root of 5. And then if we divide that by the height, which I remind you is 2, we see the perfect golden ratio, 1 plus the square root of 5 over 2. So this really is, in fact, a perfect golden rectangle, and that's the construction. I also want us to think about the golden rectangle in another example that we saw in architecture in the French villa designed by Le Corbusier. And the image that you're seeing right now is, in fact, of that French villa. And remember that if we put a large rectangle around the villa, including the topmost parts of the chimney and the roof, what you see, in fact, is a perfect golden rectangle. And as we mentioned in the previous lecture, that is, in fact, extremely deliberate. This was not coincidental. It, in fact, is exact and deliberate, since Le Corbusier actually perceived mathematics to be soothing to the human spirit. He actually tried to embrace mathematical ideas and incorporate it into the surroundings, in this case, the villa. Now, if you look at the villa or return to this image, you'll see something interesting. Remember that in our construction, we started with a square, and then we added on some stuff, almost like a little addition, if you will, to make a beautiful, perfect golden rectangle. Let's take a look at Le Corbusier's villa one more time. If we look at the villa, we see something sort of interesting. If you look at it, what you see is on the right portion is the villa, and in that left area, we see, in fact, a patio, outdoor patio region. If we were to draw a line where the actual interior of the villa resides, so draw a vertical line down to separate the interior portion of the villa from the exterior patio, you'll notice that the interior portion of the villa, in fact, is a perfect square. So, in fact, Le Corbusier has actually done a little bit more. He's actually captured this construction. Do you see it? Because the square is the interior portion of the villa, and then this rectangular portion here, you see, is in fact the patio. So he's actually even captured the construction, which is quite fascinating. But now let's actually take a look at that patio, or correspondingly to this rectangle right here. And in fact, on the image you're going to look at, what I did was I just took the patio, put it on its side, and enlarged it to be the same size as the original villa. So I just sort of increased the magnification of that picture. Now, I want you to look at that rectangle, and I'm going to ask you to see if you are drawn to it. Or in this image, I want you to look at this rectangle. The little rectangle that we had to add on to the square to make the totality a perfect golden rectangle. In particular, maybe this is a little bit funny to do, but I'm actually going to put this on its side. But now I just want you to focus on this. Just focus on this. What do you think about that rectangle? Do you like it? Do you like it? Well, in fact, this, I claim, is another perfect golden rectangle. So in order to make a perfect golden rectangle, we take a square, we do this construction, and we add on a rectangle to make a totality of a huge golden rectangle. But the rectangle that we had to add on, I claim, is another perfect golden rectangle. Or in the image of the villa by Le Corbusier, if you look at the patio portion and put the patio on its side, what do we have? We have another perfect golden rectangle. Now, first of all, let's just ask ourselves, why is that true? Why is that true? Well, let's just verify it. So here we go. Let's look at the image that we have here. We're going to look at this rectangle, and I'm going to want to look at base divided by height and see if, in fact, it has the right ratio. But now remember, this rectangle is sort of on its side, right? We think of the rectangle really as being like this. So the base here is going to be this, and the height will be this. Well, what's the base? Well, I'm going to turn it back again. The base, which is currently this length, is 2. So let me come back here and just write 2 here. The height of this rectangle, well, let's turn it back one more time and see what that is. Well, that corresponds actually to this length right here. Well, what is that length right here? That might seem like a difficult length to compute. Maybe we need some sort of highbrow mathematics, but not at all. Because I remind you that this entire length here actually is the square root of 5. And we know this length to be 1. So this length is easy to compute. It's just the square root of 5 once I subtract the 1. So in fact, this length is just the square root of 5 minus 1. So if I turn this back for one last time, what I see here is that this length is the square root of 5 minus the number 1. Well, so therefore, what is the ratio of base to height? Well, that's going to be 2 divided by the number square root of 5 minus 1. Well, wait a minute. 2 divided by the square root of 5 minus 1 does not, to me, sound like the golden ratio. It does not sound like 1 plus square root of 5 divided by 2. So this does not sound good. But here's a great experiment that I invite all of you to try. Plug this number into a calculator. That is, let's take 2 and divide it by the quantity square root of 5 minus 1. If you actually want to try this, by the way I suggest you do it, unless you have a very fancy calculator, is first compute the square root of 5, then subtract the number 1, and then store that number in memory or something, or write it down, and then take 2 and divide it by that number, and push the equal sign. You know what you get? Turns out you get 1.618033989. Boom, 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 boom. It corresponds perfectly to the decimal expansion for the golden ratio. Well, okay, but this is fantastic, because if this is a golden rectangle, then if I cut off the largest possible square that I can, then I'm left with a little rectangle here, and what about that rectangle? Well, it's a golden rectangle by the exact same principle. I start with a big golden rectangle, cut off the biggest square, I'm left with a golden rectangle. Repeat. Cut off the biggest square, I'm left with another golden rectangle. I can actually repeat this again. Cut off the biggest square, I'm left with a golden rectangle. And if I were to do that, what we'd get is a fantastic image that would look like this. I cut off this square, I get a golden rectangle. I cut off this square from the golden rectangle, I get another golden rectangle. I cut off this square, I get another golden rectangle, and I can keep doing this. Now, the really neat thing is that this regeneration property might actually provide an insight into why this rectangle is so aesthetically appealing to us. It has this regeneration feature. And in fact, this is the only rectangle we can draw that has this property. That if you cut off the square, what you're left with, in fact, is similar to the entire original whole. So this might explain why we're drawn to it somehow. There is no other rectangle that has, in fact, this property. So this might actually be a potential mathematical explanation for why people have been drawn to it throughout humanity. Well, but now armed with this, you may remember that we had these circle arcs. If this, in fact, is a square, I could actually draw, if I wanted to, an enormous quarter of a circle. Since this is a square, I could actually put in a huge quarter of a circle. And let me just do that for you. And you can see that, it, of course, since it's a perfect square, this quarter of a circle fits perfectly in. But now this is a square, and I can put inside of it a quarter circle. Much smaller, of course. Now this is a square, so I can put inside of it a quarter circle. Well, this is a square, so I can put a little teeny quarter circle in there. And this is a square, I can put in a little quarter circle in here. And here's a square, I can put a little quarter circle here. And you can keep repeating this process if you want. And what you generate is a really beautiful spiral. So this spiral curve is sort of a spectacular curve that's naturally coming out. Sometimes this is referred to as the logarithmic spiral. And in fact, my producer generated a beautiful picture of this, which I'd like to share with you. And you can really see that spiral just spiraling in quite a spectacular fashion. In fact, by the way, this has been the inspiration for many things. First of all, for in the art world, we've seen reflections of this. In fact, it is said that this particular curve was Matisse's inspiration for his painting, his work rather, L'Escargot. And if you see that beautiful collage of colors where he's trying to capture the beauty of this spiral. So in fact, art, in fact, is inspired by this mathematical object. But in fact, so is nature long before Matisse. In fact, if you've ever taken a look at the nautilus shell, you see a curve of this kind. And in fact, it even becomes more intriguing when you cut it in half and you compare. It really is beautiful to see how closely nature conforms with the mathematics that we're discovering. All from the golden ratio, all from the golden rectangle. So there's some beautiful reflections in this object. Anyway, I think that's just a beautiful image to reflect on and to enjoy, and also to see reflections of it in nature. Okay, well, certainly we all know that mathematics is serious business and certainly a hard science. But sometimes it can also cross the line into mathematical myth and even mischief. And I wanted to illustrate some of these issues with some silly examples. You see, some people actually, see great things in their tea leaves and so forth, and other people actually see reflections of the golden rectangle everywhere. Another wonderful example of this in the art world is Le Corbusier's wonderful ink drawing from 1946 called Modular, where he tries to take the body, the human figure, and partition it with Fibonacci-type patterns in order to try to capture proportions that conform to the golden ratio. So, for example, if you look at that figure, this is the image that he drew. You'll see numbers that he put there. Those are numbers that he put. This is, in fact, the original image. But if you look in the very, very bottom, in that first column, that left-hand column, and you read from the bottom up, you'll see that he's marking things like the height of the toe and the height of the foot and the ankle and so forth. And look at those numbers. I don't know if you can read them, but I'll read them to you. The very bottommost one is a 6. The one above it is a 9. The one above it is a 15. And notice that 6 plus 9 is 15. The next number up is 24, which you'll notice is, in fact, 9 plus 15. Then above the 24 is the 39, and so forth. The pattern continues. This, in fact, is an example of a recurrent sequence with different starting seeds, but the same generating process. So in fact, we know that the ratios will in fact conform to the golden ratio. So again, very deliberate. You also notice that the belly button there is marked. You can see that in the center of the figure. And in fact, this brings up a funny myth, which is that if you actually were to measure the height from your feet up to your belly button, and then the height from your belly button up to the top of your head, and look at that ratio, it should be a golden ratio if you are the ideal proportions. Well, in the privacy of your own home, you can see how close you come to the ideal if you believe this. And certainly this is not at all scientifically or mathematically proven, but certainly it is reflected in Le Corbussier's work. Well, okay, so do we see the golden rectangle or not? Certainly we've seen many examples in the past 2 lectures where artists and mathematicians have actually incorporated this figure and these proportions and the Fibonacci pattern certainly deliberately in their work. In the case of the golden rectangle, what we saw was the essential feature of the golden rectangle was that it had this regeneration property. If you were to cut off the largest square you possibly can, the remaining smaller rectangle, in fact, is another example of a golden rectangle, and you can repeat that process. That essential feature, which only the golden rectangle possesses, might in fact be an explanation for why this is so appealing.
It's a most remarkable shape. It can mathematically reproduce itself indefinitely. All these rectangles have exactly the same proportions. This figure also contains a magic spiral that repeats the proportions of the golden section into infinity.